Hello and welcome to this tutorial on designing and simulating a microring resonator based polymorphic electro-optic logic gate using Ansys Lumerical suite. Firstly, let us understand the structure and other relevant details of this device. This microring resonator based polymorphic electro-optic logic gate is an add-drop microring resonator with 4 quarter-sized phase shifting sections embedded inside it, as you can see here. Two quarter-sized sections of this device are two PN junctions which operate in forward bias condition, whereas the remaining two quarter-sized sections integrate microheaters. The cross-section of a PN junction-based section of this device is shown here, which is basically a ridge waveguide with an embedded lateral PN junction fabricated on the top of a buried oxide layer. The dimensions of the p-type and n-type regions and their corresponding carrier concentrations are also provided here. These PN junction based sections of this device work as input terminals where the input logic signals are applied. Now, on the other hand, the microheaters integrated sections of this device work as programming terminals that are used to program this device to perform specific logic and complementary logic functions. Now, to design and simulate this device using Ansys Lumerical suite, we have to break this device down into a set of primitive elements, as you can see here. We use different solvers in the Ansys Lumerical suite to model each primitive element. From these models, we extract various parameters corresponding to each primitive element. Later, we combine all of the extracted parameters in Ansys Lumerical's interconnect tool to create this device. Then we perform the frequency domain and time domain transient simulations of this device. Now, before we jump into any simulations, firstly we have to classify which primitive elements are passive and which are active. Now, as you can see here, the straight waveguides coupled to this microring are passive. Now, these straight waveguides can be characterized using the finite difference eigenmode solver in the Ansys Lumerical suite, from which the effective index, group index, and dispersion for the waveguides as functions of wavelength are extracted. Similarly, the coupling sections here at the top and bottom are also passive. These coupling sections can be created in the finite difference time domain solver, from which the power coupling coefficients as a function of wavelength for the fundamental TE mode are extracted. Now, coming to the active devices. The PN junction based input terminals and the integrated microheater based programming terminals are active devices since they require an external source to function. Talking about the PN junction first, this can be modeled in the charge solver of the Ansys Lumerical suite, from which the spatial distribution of charge carriers in the PN junction as a function of bias voltage is extracted. Then that data is exported into the finite difference eigenmode solver, and the perturbations in the index as a function of the bias voltage are created. Now, the integrated microheaters can be modeled in the heat solver of the Ansys Lumerical suite, from which the temperature profile of the microring as a function of applied microheater voltage is extracted. Then this data is exported into the FDE solver to calculate the change in index as a function of temperature. Finally, we create compact models corresponding to each primitive element based on the data extracted from each of their simulations, and then combine all of them and create the microring resonator based polymorphic electro-optic logic gate in the interconnect tool of Ansys Lumerical suite. And then we perform the frequency domain and time domain transient simulations to validate the functionality of this device. In the first step, we model the coupling section of the device and extract coupling coefficient for a certain gap size between the waveguide and the microring. As we can see here, this structure is a waveguide coupled to a half ring. Here we have added the FTTD and ports to extract S parameters corresponding to the coupling section. We do this by adding the S parameter sweep in the optimization and sweeps window. If we open this, as you can see, we specified the names of the ports which we have added to the structure here. After we extract the S parameters, we run the script which takes the generated S parameters as input and calculates coupling coefficient in the form of percentage for different wavelengths. Firstly, we'll simulate this structure using FTTD. Let's do that. The simulation has completed. Now we'll run the S parameter matrix sweep to generate S parameters for this structure. The S parameter simulation has finished. Now let's run this script here. Before that, if you keenly observe in the script, the calculated coupling coefficients are actually saved into this file in the same folder where the simulation file is stored, which we'll use later in the interconnect. Now let's run this. As you can see, the coupling coefficient here on y-axis in percentage versus wavelength. You can also change the distance or the coupling gap size between the waveguide and the ring resonator and repeat this process to get different coupling coefficients. In this step, which is step 2, we will model the passive straight waveguides in Mode tool. As you can see here, we have created the RIB waveguide structure. We have added FDE solver to simulate this structure. Let's go ahead and run this. Now the simulation is done. Now let's do a frequency sweep to generate parameters such as refractive index, group index as a function of wavelength. The frequency sweep simulation has finished. Now let's save the data to a file so that we can use it in our last step of assembling the circuit in the interconnect tool. For that, click on the data export here and click on export for interconnect. and save it in your desired folder. Now the earlier simulation we did was actually for a passive straight waveguide. You can do the same for the passive bent waveguide by enabling the bent waveguide option here and provide the desired radius, let's say 15 microns, and then follow the same procedure as straight waveguide simulation which we did previously. In this step, which is step 3, we will firstly model the lateral PN junction in charge tool, from which we extract spatial distribution of charge carriers with respect to applied forward bias voltage. As you can see here, the rib waveguide structure and also the lateral PN junction modeled under the charge solver, which has N-type and P-type silicon with carrier concentration of 10 power 17 per centimeter cube. And the lightly doped N-type and P-type silicon with carrier concentration of 10 power 18 per centimeter cube. We also have a cathode and an anode terminals to apply the bias voltage. We can specify the desired voltage range and step size here. For this simulation, we will be using 0 to 1.5 volts with a step size of 0.5 volts. We have also added this monitor here to save the data generated from the simulation. This data will later be imported into FDE solver to generate change in effective index versus bias voltage. Now let's run the simulation. The simulation is done and the change in carrier density versus bias voltage has been saved to a file specified in the monitor window here. Now in the FDE solver, create the rib waveguide structure and add this NP density grid, which can be added from the attributes here. Now this NP density grid dimensions span across the rib waveguide. In this NP density grid, let's add the data file generated from the earlier charge simulations. Since the quarter size phase shifting sections in the device are bent waveguides, we have to enable bent waveguide option here and provide certain bend radius, let's say 15 micrometers. Now let's do the modal analysis and frequency sweep and then save the frequency sweep data to use it in the interconnect later. Now the frequency sweep is done. Let's save the data into a file so that we can use it later in the interconnect. Now to calculate the effective index versus bias voltage, we have to add this parameter sweep in the optimization and sweeps window. In this parameter sweep, we have to specify the voltage range, which is 0 to 1.5 volts, the step, and the wavelength at which we would like to find the effective index versus the bias voltage. Also, after the sweep is done, to save the data, we have to add this parameter to the results window. Now, instead of directly running this sweep simulation here, we will run this code that performs this sweep and also generates the change in real and imaginary part of effective indices versus bias voltage, which will be saved to this file as you can see here. This data will be used in our last step where we assemble the circuit in the interconnect tool. Now as you can see, the sweep simulation is done and it has generated the change in real part and imaginary part of effective index with respect to the bias voltage. In this step, which is step 4, we will firstly model a microring with an integrated microheater, from which we generate the change in temperature versus the voltage applied to the microheater in the heat solver. Later we will import that data into the FDE solver, where we will generate change in effective index with respect to change in temperature. As you can see the structure here, we have a ring resonator underneath the heater, and we also have a nichrome heater with gold contacts created in the SiO2 layer. We specify the voltage range here in this voltage boundary condition. Now let's run the simulation. The simulation is done. Now let's run the script which calculates the temperature change in each quarter of a microring resonator with respect to the applied voltage and saves it to a file. Now as you can see, the simulation is done and all this data has been saved into a file which we will later use in the interconnect tool. Now we create a ring structure in FDE solver, and we have also created this temperature sweep in which we sweep the temperature of the ring at different voltages which we generated earlier from the heat solver. Firstly, we will run the modal analysis. Now we will run the sweep to calculate the effective index for different temperatures of the microring resonator. Now we will run the script which takes the effective indices generated for different temperatures of microring as input and calculates the change in real and imaginary part of effective index with respect to temperature. As you can see here, this data will be saved into this file which we will later use in the interconnect tool. In this final step, which is step 5, we will assemble this circuit in the interconnect tool. Firstly, we'll start with creating compact models for passive devices, and then we will move on to active devices. For passives, as we know that we have coupling section and straight waveguides. To create compact models for these, add directional coupler and straight waveguides from the element library here. You can simply type coupler here, and you can see here this is the waveguide coupler, and then you can also type mode waveguide, and then this is your straight waveguide element. Now to create compact models, add the data files which we have generated from first 2 steps of our simulations to these elements. For the directional coupler, you can upload it here. And then for the passive straight waveguide, you can upload it here. Coming to active devices, which are PN junction based input terminals and the microheater based programming terminals. Firstly, we will start with creating compact models for 2/4 of PN junction based input terminals. For that, we have to add 2 optical modulation elements which can be found in the element library here. As you can see, this is the optical modulation element. And then we have to add two straight waveguides, which can also be found in the element library. Now to the two optical modulation elements, we have to add the data file, which has change in real and imaginary part of effective indices with respect to applied bias voltage, which we have generated in step 3. Let's add that. To the waveguides, we have to add the frequency sweep data file which we generated from the step 3 of the simulation. Let's add that. We also have to add DC sources here to the optical modulation so that we can apply our desired bias voltage. Now moving on to creating the compact models for integrated microheaters based programming terminals. Similar to the PN junction based input terminals, we have to add two optical modulation elements here, which can be found in the element library. And then we have to add two straight waveguides, mode waveguides, which can also be found in the element library. But here, to the optical modulation elements, we have to add the data file which has change in real and imaginary part of effective indices with respect to change in temperature, which we have generated in step 4. Let's add that. Now for these waveguides, we can add the same data file which we have added to these waveguides. Let's add that. Now let's connect all the elements. We also have to add DC sources to the microheater based programming terminals here. Now we have connected all the elements. So this is our Microring Resonator based Polymorphic Electro-Optic logic gate. Now to perform frequency analysis, we have to connect an optical network analyzer to this device. This can be found in the element library here under analyzers. The output of the analyzer should be connected to the input port of the device, and the through port and drop ports of the device are connected to the input ports of the ONA. For ONA, let's choose the start and stop frequencies to be 1540 and 1550 nanometers, and we'll run the simulation for 10,000 points. Now to achieve any logic functionality, for instance, let's consider AND logic functionality, which is generated at the drop port of this device. Firstly, we have to set the voltage applied to programming terminals of this device to be 0.9 volts. And then for the input bit operands, we can apply bias voltage of 1.5 volts for bit 1 and 0 volts for bit 0. Let's apply 0, 0 first. And then we'll run the simulation. Let's collect the transmission at the drop port. And then 1 0 or 0 1. And then 1 1. Now, if we look at the transmission here, if we consider our laser input to be 1545 nanometers, then you can see the amount of transmission corresponding to 0 0, 1 0 or 0 1, 1 1 at 1545 nanometers follows the truth table of AND logic. Similarly, we can achieve several other logic functionalities such as NAND, OR, NOR, XOR, XNOR with this device. Now to perform time domain transient analysis, we have to connect pseudo-random bit sequence generators and NRZ pulse generators to the PN junction based input terminals instead of the DC sources. These elements can be found in the element library here. Instead of ONA, we have to add a laser source here that provides a certain wavelength signal to the input port of the device. We can set the bitrate here. For instance, we set the bitrate here to 10 Gbps, and let's provide a custom input bit pattern to the two PRBS generators. Now we also set the programming voltage of the programming terminals to be 0.9 volts, which is the programming voltage for AND gate functionality. We have also added optical oscilloscopes to the drop port and through port of the device. Let's run the simulation now. Now, as you can see, the output pulse signal at the drop port follows the truth table functionality of AND for the given input bit sequences here. Similarly, we can achieve several other logic functionalities such as NAND, OR, NOR, XOR, XNOR with this device.